Just let us introduce you, and then you can share the screen and you can proceed. Okay. So first, I would like to invite all the participants, our panelists and esteemed speaker on the day 5 and second session of day 5. And in this session, we have 2 lectures. The first one will be delivered by Dr. Soumodipta Rokshit. He's presently in Spain, so he will be delivering from abroad. And to introduce him, may I request Professor Subhas Chandra Bhattacharya sir to introduce our speaker.
Yes, it is the custom to introduce speaker. Thank you, Tapos. Now, Dr. Soumodipta Rokshit, having completed her master's and PhD from Jadavpur University, moved to IIT Bombay as postdoc fellow. His work placed him in a high position. He is working on photocatalysts and nanomaterials, and their publications is very good. Now, from Bombay, he achieving Marie Curie Fellowship, moved to Spain, University of Castilla-La Mancha, Spain. In his young age, he published more than 25 articles, papers. His current research interest is on quantum dot, perovskites, nanomaterials, of course. And most of his papers have attracted attention from various quarters, indicating the importance of his work. He is working on, I told you, and he worked on also soft synthesis of nanomaterials. Now, with this brief introduction, I request Dr. Soumodipta Rokshit to deliver his lecture.
Thank you very much, sir, for this kind introduction. I mean, this is a privilege, you know, being introduced by your PhD supervisor is kind of a privilege. And I really want to thank the organizers, Dr. Tapos Ghosh or Dr. Arijit Bag and Dr. Devashree Manna as well. I recognize Dr. Devashree Manna. Actually, she was a senior in my university, in Jadavpur University.
Yes.
Yeah. So nice to meet you all. Okay. With this, I want to share my screen and start my lecture. Okay. So, can you see or no?
Yes,
yes, it is visible.
Need to be full screened.
Okay. Okay. So today the topic of my lecture is insights into the carrier dynamics and sensing mechanism of water-soluble quantum dots. This is the picture of our university. Is a very old building. I mean, the whole university is basically situated in the building like is from 18th century or so. So it's full of history. And the Toledo, I live in Toledo, and the Toledo itself, the whole city is basically World Heritage Site right now. So you can understand it's a very good place to stay. Okay. So let's start with the basic things first. That what is quantum dot? Now, from people have started with the atom and bulk semiconductor molecules and all these things, and now we have moved to quantum dot from those avenue, and basically quantum dots can be defined as the class of materials in which the quantum confinement can be evidenced. Now, what is quantum confinement? That the electron, we'll talk about the excitons and later, and the sizes of this. When we say quantum dot, we basically talk about semiconductor quantum dot. Not, I mean, and they should have what can I say? The size dimension from 2 to 10 nanometer. but you have to understand that not every nanoparticle, every kind of nanoparticle having the size of 2 to 10 nanometer is a quantum dot. Quantum dot is basically, we are referring to semiconductor materials like cadmium selenide, cadmium sulfide, cadmium telluride, indium phosphide, zinc selenide, zinc sulfide, all these things. Okay, why this quantum dot is so lucrative towards for scientists and all? First and foremost is their optical properties and their electronic properties. Now, for and when we say optical properties, we mean fluorescence. Now, if you say fluorescence, the first things comes into our mind is basically molecules. Now, people has examined various kind of molecules and all these things for different applications and all. But the main problem is that their stability and the photo bleaching. Now, these two effects has restricted the application of several very good molecules. I mean, they can be applied, but due to these two constraints, they cannot be applied as vividly as they should have. So, from the 1995 or something like that, this quantum dot came into the market. So the main attractiveness of this kind of semiconductor quantum dot is their stability, photo stability. They are very stable, and let me tell you that their optoelectronic properties, since they are semiconductors, they can easily, what can I say, transport electrons and all these things, and they can be easily applied in LEDs, solar cells. Right now, this era, people are saying this is the era of perovskites. But the problem is that they are also not that stable like quantum dot. Quantum dot solar cell is still much more stable than the commercial perovskite solar cells still. So, and the second one is phototunability. So when we change the size of a quantum dot, we actually changing the band structure. So the band gap between the conduction and the valence band becomes higher and higher when we are decreasing the size of the quantum dots. And basically what is that we are confining the electron and the hole pair more into the system. So the bandage gap is increasing, and therefore the emission gets blue shifted. So when for cadmium selenide, it was published by Professor Bawindi in MIT in 2000 or so, that how the size of CDAC quantum dots from moving from 8 to 2 nanometers changes the entire spectral range from blue, red to blue. This is a picture of the quantum dot solutions from blue to red, as you can see. Now, when we say quantum dot, normal quantum dot has a problem. The problem is that bare quantum dots are not as stable as should be, because there are surface traps, there are interaction with the surface, and therefore normal without any protection or something, normal quantum dots are not that stable. So what people do, people put a shell, stable shell over the quantum dots to make it more stable. Now, depending on the structure of the core shell structure, quantum dots can be classified into 3 classes, like type 1, type 2, and quasi-type 2. Now, what is type 1? Type 1 here, what do you do? We put a core quantum dot, and then we put a shell over it. Now, what is the band structure of the shell? This is very important. Now, the band gap of the shell should be much more than the core. And here you can see we can have different kind of shell structure for zinc sulfide or zinc selenide or cadmium sulfide. Every shell has a different purpose to serve. First of all, if we coat with zinc sulfide, what it does, it prevents the exciton leakage, and therefore, what can I say? The quantum will also increases. For type zinc selenide, now what happens is that the valence band leads to a better exciton gap, and therefore the quantum will increases more than zinc sulfide. For CDS, they expand the conduction band efficiently, and the extent of increase of the quantum will is not as much as the zinc sulfide or zinc selenide. So you can see sometimes people put zinc sulfide and zinc selenide both shell to obstruct the exciton leakage and basically extending the valence band range. Now type 2. Here in type 1, the conduction in the shell band was higher than that of core. Here, in case of the shell band gap is lesser than that of the core. What happens then? What happens that the excitons here, the exciton generated now can relax to the shell, and therefore from the shell structure it emits. So if we have a green emitting quantum dot, due to the type 2 shell structure, it can emit in the orange or red section. So we are basically increasing. We are basically not decreasing the band gap and getting a red emission. And the last of all is quasi-type 2. Now, quasi-type 2 is basically when you are putting a thick shell over a quantum dot. Here I showed a CDT, CDS quantum dot. The thing is that here at least one electron is totally delocalized within the core and the shell system. And that means this thick shell can be tuned to make this quasi-type 2 to type 1 or type 2. So you can actually vary from this to other two structures. Now, before going to my work, I want to talk about, since Professor SCB sir told me that most of the participants here are students, I want to give them a very brief introduction of transient absorption spectroscopy, because without telling what is transient absorption and what we are looking for, even if I show the results, that will have no meaning. So let's start. Before that, what is exciton and all these things? First, we need to see. So in a quantum dot, what we have? Valence band and conduction band. So when we excite the quantum dot, what happens? Electron goes to the conduction band, and therefore the electron pair produced. So this electron hole pair is known as exciton. Now, I heard many people have this misconception that when you say exciton means excited state electron or something. But no, exciton doesn't mean excited state electron. Exciton means the electron and the hole pair. And you have to remind this, because this electron hole pair, you can what can I say, explain it in terms of particle in a 1D box. So this is known as the band gap. This is a 0 point vibrational energy level of the excited, and this is of the hole. Okay, let's go to the transient absorption. So when we have a molecule, when we have a sample, what we do is put the sample in a rotating cell, because we are going to excite it with pulse lasers. So what happens first? We excite the sample with very short pulses, high energy short pulses. Those are femtosecond pulses. So what happens? Some of the molecules get excited. Now you have to understand the rotating cell. For the rotating cell, the diameter is around 3 centimeters or so, and the spot size of the laser is more or less 200 to 250 micrometer. So a very low fraction of the molecules get excited. So this is kind of exaggeration of what we have actually, but still to understand properly, we need to show this. Now the molecule is excited now. So what do we do next? We wait. Now the waiting of the time is very, very short, but still and with that delta time, we put a delay. With that delta time, some of the molecules get back to the ground state, and some of the molecules still at the excited state. Then what we do, we probe these molecules with a white light. White light means it's a mixture of all lights, and therefore it's basically a spectrum, and the intensity is very low, so it cannot further excite the other molecules as well. So what we do, so the excited state molecules take up this white light, absorb it, and give some absorption. So basically what we are seeing a snapshot of the excited state behavior of a sample. So how we are going to do this? Let me show you. So when we have, okay, so one thing, this excited state, this laser by which we are exciting the sample is called as pump, and the white light by which we are probing the system is called probe. So this is pump and this is probe. Then, so suppose that delay has a very key role to play, this delta t. So when the probe is coming before the pump, so white light is going, and laser, blue laser, I mean excitation laser is also going. So before that there is no excitation, okay? But when the pump and the probe goes at the same time, so we are exciting the molecule and we are probing at the same time, what happens? The molecules get excited. Now, at a time difference, then right now we are giving the delay. So at delta t, again we are exciting the molecule. Then again molecules. Now at delta t, some of the molecules again goes to the ground state, and some of the molecules are still in the excited state, and we are taking the snapshot of those molecules. And now if we give the delay further, so we are getting like this. This is the kinetics, and our life would have been much simpler if we get a single exponential decay. But in any molecule or in any quantum dot or any other system, there are several radiative and non-radiative things are going on. So you will get a multi-excitonic, not multi-excitonic, sorry, a multi-exponential decay. So with that decay, you will have time scales, and from time scale, you will assign those time scales to different processes, and you will get to understand what process is going on. Now, again, before going to actual data, we'll see how the signal of transient spectra comes up. Okay. So this is a kind of typical transient absorption spectra of any molecule or quantum dot or so. So here we plot delta A versus time. Time means delay. So delta A is basically differential absorption. What is differential absorption? Differential absorption is that when there is no pump, what is the absorption? And then what is the absorption due to the pump? Pump means after the excitation. Okay, let's see what is happening and why this kind of negative and positive data is there. Okay, let's suppose this is the typical ground state of a molecule, and then if you excite, it goes to the excited state, and then what we have excited state. We have electrons in the excited state. So you have to understand the population in the ground state is not the same after the excitation. So the ground state population has now depleted. Now, if you consider this delta A, now suppose when A absorbance, when there is no pump, because absorption is directly proportional to the population. So when there is no pump, there are more population at the ground state, but when pump is there, when we excite it, some molecules go into the excited state, so the ground state population has depleted. So the A pump will be less than no pump, so hence we'll get a negative band, and this is to be known as ground state bleach. Another thing can happen. Now, when the molecule, when the electrons are in the excited state, if you excite, now those excited state molecules can be excited further by the pump, and what happens? They can go down to the ground state to show emission. This is called as stimulated emission. Now, again, why stimulated emission is now in the negative side? Because when there is no pump, because right now this is the zero time, this is the zero case. So when there is no pump, the population at the excited state is high. When there is pump, population of the excited state is much less. So we'll have a negative C. Now, I want to remind you that for this case, what happens is that most of the time, you cannot distinguish between ground state bleach and the stimulated emission, because you can see the stimulated emission is the signal should be much weaker, because at the population at the excited state is much low, and there are other processes that are happening as well. So stimulated emission, in very few molecules, you can see the stimulated emission. Now, another case can happen that when you excite, when you are exciting, the excited state, excited electron gets further excited, and when it gets further excited, it gives a positive signal. Now, why this is a positive signal? If you see, when there is no pump, what is the population density at the higher excited state? 0. There is no population. But when there is a pump, there is a population. So delta A should be positive. Okay. So I think you have a small idea about what is ground state bleach or stimulated emission or excited state absorption. Now we'll go into our experimental details. What is our idea? So the objective of our work was synthesizing quantum dots in water, water-soluble quantum dots. Now, you can synthesize water-soluble quantum dots in 2 ways. Number 1 is synthesize quantum dots in oil medium, and then by ligand transfer it to the water phase, or synthesis the quantum dots is directly in water. Now, the first one has a major problem. The problem is that there's a loss of considerable amount of quantum, because water deactivates those quantum dots, because ligand exchange is not 100%. It cannot be 100%, and there is a quantum yield loss as well. So what we did, we took a branched polymer, that is a dendrimeric polymer, that is polyethylene, which has a molecular weight around 25,000, and we synthesize this cadmium sulfide quantum in water in room temperature. Okay, so these are 2 main things. First, we synthesized in water directly, and number 2, So since we have synthesized in water, there is no question of ligand exchange. And number two, this is in room temperature. Okay. So what we got, okay, first, then we characterize the quantum dots via 10. We measure different, what can I say, we got well-defined crystal planes, which can be ascribed to the different cubic zinc plane structure of the cadmium sulfide. Now, look, cadmium sulfide is a very old quantum dot. It's very well studied. But the thing is that after 2010 or something, the research on this cadmium sulfide has just stopped. I don't know why, but people are not doing, were not doing this, working on this. They are much more interested in cadmium sulfide, cadmium selenide, cadmium telluride, indium phosphide, indium arsenide, arsenide, and others quantum dots. So next, you can see the fluorescence, the emission of the quantum dots, although it looks like yellow, it's basically greenish yellow. The emission is around 515 or something like that. So you can see this is the absorption spectra of the quantum dot, and which we have 3 peaks which can be ascribed to the band. So this is X1. So like the first, what can I say? So when this first peak on 2.87, this is due to ground state to X1, and the other peaks is for the higher excite state absorption. And when we excite at 2.87 electron volt, then we got a emission, broad emission. Although it's a greenish yellow emission, the emission is not like CDAC or CET, is not sharp. The FWHM is quite high. So it's very, it was already known that in water-soluble quantum dots, surface traps has a very major role to play. So basically, the surface traps and all the other things are going on, and we can have broad emission structure. So what we did, the PL transient shows 3 times. So there is around a very fast decay of 0.6 nanoseconds, which is 75% of the amplitude, and there's another one 7.3 and around 50 nanoseconds. So this can be ascribed to shallow and deep trap states of the quantum. Now, the thing is that what is happening there? Why, although in presence of the surface traps and all the other things in water, why we are getting so good emission? Because 36% quantum is frankly very good for water-soluble quantum dots. So what we did transient absorption spectroscopy. As you can see, this is a pure. If you can remind what I said, this is a ground state bleach, and this is a Photoinduced excess absorption, all this stuff. Although this is much less, but still is there. So let's talk about the bleach kinetics. So when we are talking about bleach, we are talking about the electron sounding. Now, what happens when we are exciting? The electron goes to the conduction band, and those electrons are known as hot electrons. Then the hot electrons can directly goes to the electron traps, which is known as hot electron trapping, or the hot electrons gets interband relaxation will happen, and then from relaxed state, although it's in excited state, in a relaxed state, it can go to the electron traps, and this is known as cold electron traps. So these are the trapping processes, what is happening, and you can see that from the kinetics of this bleach, we can see the time scales that interband relaxation occurs at around 400 femtosecond, hot electron trapping comes around 1.2 picosecond, and cold electron trapping is rather slow, 11 picosecond. Now, why do we say this is happening? Because when we are exciting the quantum dots far from the their bandage excitation, we are getting a steep decrease of photoluminescence quantum rate. This is because of the electron trapping. If the students are listening, if they want to get a very clear picture, I would encourage you to read Professor Klimov's review paper in Annual Review of Physical Chemistry. It's a fantastic review. You should read it, and you will get to know what are the process and how is happening within a quantum. Okay. Now, the second thing is going on is multi-excitonic Auger recombination. Now, you have to understand, Auger recombination is although it's a recombination process, it's non-radiative. What happens? You excite the electron, then electrons goes up, and through intraband relaxation comes to the lowest vibrational energy level of the excited state. Then what happens? It can recombine. When it recombines, it loses some energy. That energy is not radiative. It's a non-radiative energy, and that energy actually excites the other electrons in the excited state to goes up to the higher energy level. And this is called Auger recombination, and this happens around 30 picoseconds. And how do we know that? We did a fluence dependence study of that. So with the increase in pump fluence, we are actually the kinetics is getting faster. Now here you can see delta N. Delta N is basically the average number of excitons produced in that due to the pump in that system. As you can see, when you increase the average number of excitons, you are actually faster kinetics, which basically shows multi-exciton relaxation and trapping contributions as well. Now, the last part, what is the, as you can see, this part, there's a very, what can I say? There's a very low amount of positive signal, but still signal is there. And that is to be known as photoinduced absorption. And so, when you are talking about photoinduced absorption, you are talking about holes only. So what happens? If you excite the electrons, it goes up, and at the same time, hole can be trapped as well. Hole can be trapped, and this occurs around less than 200 femtoseconds. And then the hole in the trap and the vibration level goes to the higher energy level. Now, the thing is that when people say that hole is occupied or something, this is not the movement of the hole, maybe movement of the electron. Basically, what happens, the hole is in the lowest energy level. The other electrons are the high energy level. So they go to the hole and the hole moves down. So this gives a positive signal, which also can be found through fluence dependence kinetics. So what is happening? So what we have is intraband relaxation at around 1.2 picosecond. We have shallow trapping of 11 picosecond, deep trapping of 130 picosecond, and Auger recombination of 29 picosecond. All these things are going on, and it gives us a good quantum area. And actually, what is happening? Participants can now see. Okay, yeah. So the thing is that all the things is going on, and this is a kind of well-defined what is multi-excitonic relaxation processes in water-soluble CDS quantum dots. Okay, so we have produced very well-luminescent water-soluble quantum dots. What about the application? First application, it comes into mind that sensing. Now, biocompatibility, so we can apply to different biosystems as well. But let's our perspective was not get into the bio section, rather to work on sensing. So because sensing is very important for water pollution. And number two is selectivity, because now in molecules we have seen a lot of sensing research on a lot of sensing is happening, and people are synthesizing different what can I say, metal ion selective molecules and other things. So selectivity is a major issue. But our main concern was, if we have a sensing, if we have a selectivity, what is the mechanism of action? Because people normally show that this sensing is happening, this is the selectivity, and do some what can I say, real sample application or something. But very few papers are there on how the sensing is happening, why they sense selectively, or the mechanism of action. Now, for quantum dots, three kinds of mechanism of action can happen. Number one, surface modification. Number two, charge transfer. Number three, energy transfer. So what we did, we understood, we wanted to understand what is happening here. Now, we didn't get any change in the absorption spectra due to addition of lead or any other ion. So basically, there is no possibility of the surface modification. Now, if we get the absorption spectra of lead 2+, you can see there is no overlap between the lead 2+ absorbance and the cadmium sulfide PL, and so there is no possibility of energy transfer. But in presence of cadmium, in presence of lead 2+, the lifetime decreased rapidly, and you can see the photoluminescence is totally quenched. This is an indication of the charge transfer. Okay, so this is the okay. So with addition of the Pb2+, you can see there's a severe quenching of photoluminescence of the cadmium sulfide quantum dots is more than 85%. And when we plotted the Stern-Volmer plot, it's totally nonlinear. We then plotted the modified Stern-Volmer plot, and it was still nonlinear. So there is something going on which can be explained through the conventional way. So, and the quenching constant is abruptly high. It's around 10 to the 15 second unit. So what is going on? And you can see if you plot fluorescent intensity or tau 0 by tau, both has nonlinear behavior in Stern-Volmer plot. So basically, quenching mechanism here is very complex. It's not as simple as that. So what we did, we again did the TA. So the TA measurement is what we are seeing, that with increase in the lead concentration, the bleach signal decreases. Now, okay, so this is the bleach signal. Now, all the bleach signals were in presence of lead 2+ at 1 picosecond delay. These are all 1 picosecond. The black one is without the lead 2+, and with lead 2+, the bleach is prominent. Why is there? Why this? Why the decrease in the bleach signal? Because of the hot electron transfer. What is hot electron transfer? Now, in presence of lead 2+ ion, a subpopulation of the conduction band gets transferred to a trap state, which actually decreases the population at the conduction band. Now, when we have a depopulation of the conduction band, we have a less signal in the bleach. This is not bleach recovery, but this is just decrease the concentration of the bleach, decrease the intensity of the bleach signal. Now, if we can see, okay, this is the kinetics part. So you can see the bleach signal, kinetics also getting faster. Okay, for the photoinduced absorption, it can be easily seen that with increase in lead-2 plus concentration, the PA photoinduced absorption signal also increases. Now, why is there? Why is that? This is basically due to the Stark effect. Now, what is Stark effect? Due to in presence of light, the electron in the conduction band goes to lower energy level and the hole goes to higher energy level. And therefore, a charge separation comes up. When there is a charge separation, you can, and there's a charge separation due to presence of lead-2 plus. So based on this observation, what we can see that we can propose a mechanism that PL quenching is due to purely surface interaction. Now, in case of cadmium sulfide quantum dots, you see that PEI is very well passivated at the surface of the quantum dot, and it can bind well with the cadmium 2+ ion, but it does not binds well with the sulfur ion, which is weakly which are weakly passivated at the surface. That gives lead-2+ ion the access to the surface sulfur atoms. When it have the access at the sulfur atom at the surface, what we are creating more hole trap states, and which is the reason we have a more positive signal in the photoinduced absorption. Okay. Now, if we see, this particular absorption of the lead-2 plus at the surface, you can plot the kind of isotherm, and it gives you the binding constant around 10⁴, which is kind of agreeable with the literature constants. So, what is actually happening? There's a thing that now the second question is the selectivity. Why it's selective towards lead? First of all, we have PEI at the surface. Now PEI has many nitrogen atoms, and it has it can donate electron to the other cations as well. So by donating the electron pair, it actually binds well with most of the metals. But mercury and the lead has a kind of complete electronic configuration, and it does not bind with the PEI. So, but people will ask, then why only lead? Why not mercury? So there are other reports as well where they showed PEI has a different kind of mechanism to bind well with the mercury as well. So basically, PEI when you put different cations, it does not have the access of the quantum dot surface due to the coverage of the PEI, and the PEI catches the cations and restricts those cations to access to have access at the surface quantum dot surface. But lead-2 plus does not bind with PEI, so it goes directly at the surface, and then this trap state created, and the recombination of the excited electron and the hole is hampered, and therefore is a charge separation, and the photoluminescence is quenched rapidly, and the ultrafast electron transfer happens around 6.2 picosecond or so. So this ultrafast electron, so what we have in conclusion, the ultrafast electron transfer is found to be the reason for the drastic quenching of the PL in the presence of lead-2 plus ions, and extremely efficient electron transfer. And since there is a charge transfer is going on, we can say we'll figure it out in future, we may have very good photocatalytic application of this kind of quantum dots. So both the works was published in JPC in 2020 and 2021. Thank you. Before ending, I wanted to show you this picture. So this is a picture of just 2 buildings away from my campus. Before, in 18th century, this campus was a arms factory. So the swords made in this arms factory was world famous, and the cannons as well. Here, there's only one place you can see Jesus Christ standing on the 4 cannons. So I was overwhelmed with this when I saw this. So I just wanted to share with this. Thank you. Hello, can you hear me?
Thank you, sir. Sir, your voice is low. Tapas sir.
Hello. Yeah.
Thank you, Rokit, for your nice, illuminating, informative talks. There are some questions in the chat box, but before that, I am asking you 2 questions.
Yes.
That is, lead can be sensed by cadmium sulfide.
Yes.
And
Cadmium sulfide quantum dots.
Quantum dots. Yeah. Oh, not cadmium sulfide molecule. It is in quantum dots.
Yes. It's in quantum.
That is another point. What is the minimum concentration of cadmium ion that can be sensed? Minimum concentration of the lead ions. Yes.
Yeah, so it's in the nanomolar region, around 100 nanomolar or something.
That is a good work, because
Yes.
During transmission of water through lead pipes, there is always a dangerous point, that is it may be toxic. So if it is in the nano range can be identified, then it is okay. Very good. Okay. Another point.
Yes.
You have shown high quenching constant, 10 to the power 18 order, 15 order.
15. Yes.
15 order. So I think there is a mixture of quenching, maybe static, dynamic.
Yeah. There's a different. I mean, there are two mechanisms are there. First, surface interaction and the electron transfer. Now, the electron transfer is very fast in the picosecond scale, the ultra fast electron transfer, and therefore this quick quenching is happening. Another thing is that when we say molecules, the molecules are when we do the sensing with the molecules are in the micromolar region. But when we do it in the quantum dots, one single quantum dot with like more like 100 or 1,000 cadmium 2+ or sulfur 2-. So basically, the concentration of quantum dot is very, very less, which gives rise to the high quenching constant.
Okay. Now go to the chat box and
chat box. Okay, why trapping contribution increases in interplay? Okay, in interplay of multi-exciton and carrier trapping. Okay, first of all, trapping is there. Look, the thing is that we don't have any surface passivation. Surface passivation means we don't have any core shell structure. We have only bare cadmium sulfide, which is covered with PEI. That's a polymer. So we don't have any band structure alignment, different kind of band structure alignment or anything. So basically at the surface, although the surface is protected with the polymer, but still it's accessible by water and all the things. So when it's accessible with the water, it can, the surface and the, as I told you, this sulfur 2- atom is not well passivated. When sulfur 2- is not well passivated at the surface, it creates the trap state. When it creates the trap state, the excited electron goes to the trap state, and actually, if there is no trap state, we have a bandage emission directly go up and goes down. We'll have 100% quantum field, but 64% quantum field is lost. So only 36%, although it's very good, but still 64% is lost. And this is just because of that not well passivated sulfur atom at the surface. I think, yeah, any question?
Next question. In the chat box, I think there are other questions also.
Chat box.
So we request to the participants and students that if you have any question, then please put your question in the chat box or in the QA section. So we are in the question answer session. So you may post your questions. You may raise your hand also to ask questions directly.
Yeah, exactly. You don't have to write, you just ask me.
Anyone from participants?
What is achieved with surface modification of quantum dots? Okay, surface modification means, look, the thing is that surface modification have different kind of aspects, like gold nanoparticle, for gold nanoparticle, for quantum dots, people modify the surface to make it more biocompatible, more water soluble, so that they can use it in biosystems. I mean, direct cell imaging or so. And sometimes they modify the surface with a ligand which has sulfur atom at the end, which can bind with the quantum dot surface, and COH at the end, which can bind with the different what can I say, different cations or different things. So therefore they can sense different cations or things. So for sensing or for biocompatibility, the surface modification is done actually.
Okay, is there any other question? Any from any participants? So
Why quantum dots? Okay, look, why quantum dots have discrete energy levels? I mean, these are well documented. I can you can find it in the, I mean, when you have quantum confinement, you will have discrete energy levels.
yes.
This is well documented, and you can find it in any book or so. There are several things you can find it.
For the properties you can find, yes.
Yeah.
Any book can be.
Yeah.
Easy. Another point, another question. Anyone? Chat box, it is in 2. What is that? Question answers 1. Does quantum confinement reduce band gap?
Quantum confinement, actually, what does it do? It actually does, it produces discrete energy level. Okay, where the question went.
Okay. That in the QA section.
Okay, yeah, fine. So quantum confinement means the exciton, right? The electron and the whole pair. So that exciton have lower distance value rather than the Bohr radius. Then only you will have the quantum confinement. And when you have a discrete band structure, you will you can reduce or you can increase the band gap. When you have small, very small size, around 2 nanometer or something, so actually the quantum confinement is much higher. So basically the band structure is much more separated rather than the quantum dots having size of 8 nanometer or 7 nanometer, where the band gap is much closer to each other. Why faster kinetics observed in interplay of multi-exciton and carrier trapping? Okay, sorry, why faster kinetics are fast? Okay, so faster kinetics means this one.
Oh, actually, ultra fast kinetics, I think.
I mean, faster kinetics where in interplay of multi-exciton and carrier trapping. I mean, okay, I think faster kinetics in presence of late 2+ is happening. So as I said, when you have the faster kinetics, we are getting it from the Blitz signal. So when late 2+ have access to the surface of the quantum dots, what happens from the excited state, some population of the excited electron goes to the trap state, and the population of the excited state becomes less, and the kinetics we getting and from the recombination, and the recombination rate is recombination is low number of excitons are now recombined. So therefore, we have a faster kinetics.
Okay. Okay. If you have any other questions, you may mail to Dr. Rokhi.
Yeah, you can please, and
Yeah.
you can and please do read our paper. And if you have any problem, you can directly email it to me. And my email is there in the paper, so you can just email it to me.
Okay. So, Dr. Soumodipta Rokhi, thank you for your illuminating and informative talk, which create interest to our students also. Thank you. Thank you very much. And I hope.
Thank you, sir. And thank you. I want to thank all the organizers, and I want to thank Professor Anindra Datta for giving me the opportunity to work on the quantum dots and all. Thank you very much, sir. Thank you very much.
Hope you will be available in the future.
Yeah, of course. For these things, I'm always available.
Thank you. Thank you. Thank you.
Thank you, sir.